Hello, everybody. Today we're going to be taking a look at another vector calculus problem that attempts to disprove the existence of magnetic fields. Um, but it fails, and we'll see why by the end of the problem. Um, so this problem could be like just a few seconds long if I were to tell you right away what the problem is. Um, but I'll take you through the process of how I figured it out. So the question asks, what is wrong with the following proof that there are no magnetic fields? And then it gives us that by electromagnetic theory, the divergence of B is equal to zero, and that actually implies that B equals curl of some A function. So these formulas are correct. Everything in green that I have written here is correct and we'll be using. So this is another way to say the divergence of B is zero, and then this is another way to say curl A equals B. And everything that has a little arrow is a vector. Um, so this is the divergence theorem, which is used in the failed proof. Um, so this says that the volume, whatever volume we're talking about, if yeah, another way to think of the divergence of B, um, yeah, the divergence of B. Nope, that's not okay. Yeah, the divergence of B is I don't know. I guess one way to say it, it's the out that the function wants to do. How out does it want to be at that point? You have a point. How much does it want to go away from that point? It doesn't matter what direction. It just matters the tendency. So, the surface, and yeah, so the volume, so if you sum the out from all of the volume, you equal the actual field out on the surface. So um, this is just a fancy way of saying something that I think is fairly obvious. If you let's say that you have a surface that's completely enclosing something, and there's nothing going through the surface. So this v dot n, um, the velocity is completely perpendicular to the normal vector. So this whole part is zero. So nothing is going through the surface. Um, that means that in total, nothing is leaving the volume, which makes sense. Um, or if something is leaving the volume, then something is moving through the surface of that volume. And that's essentially what this says. We use that result a lot in fluid dynamics. Um, because if you have a system where nothing is leaving and nothing is entering, then you know quite a bit um, about the whole situation. Okay. And then this one over here is a little bit harder to kind of visualize. The curl of a vector, which I guess in this situation we're using A. The curl is the spin. Kinda. Um, yeah, mostly. So you have a point here. The curl is the amount of spin in that small area. So if the curl of a vector field is zero, then that means there is no spinning in it. So in this case, what this is saying is so you have a curve bounding. Well, okay, we'll start on this side of the equation. So you have a surface, and it's a free open surface. You can think of like a butterfly net, how it's open. Um, so the spin, essentially what this says is the spin felt on the surface is the same as the spin felt on the curve that's bounding the surface. Or another way, with the butterfly net, the spin on the butterfly net is equal to the force felt on the rim of the butterfly net, which also makes sense if you think about it. Where else is the force going to go? Um, it's going to go into well, I mean, assuming that your butterfly net is massless and frictionless and all that stuff. Um, so yeah, so it makes enough sense if the butterfly net is spinning a lot, then the rim is going to want to spin a lot, and it would if you didn't have your hand on it. So, yeah. Now that we've gone through all that, we can take a look at what this says here. Um, so, magnetic fields, their divergence is 0. So they don't have a lot of out, or the out cancels out, I guess. So using this here, we just plug our B in for our V, right? So if the divergence is B, then the sum of all the divergence is going to be 0. No, if our divergence is 0, the sum is going to be 0, yeah. And then we just plug in this side of the equation. And then we just substitute in B for our, or not B, we substitute in for B, this here. And so this is all fine up until this point. And then it looks like we substitute this equation in here. And then since it's 0 all the way over here, then it must be 0 all the way over here. I didn't write out the rules for this, but this is still all correct from this point on. A dot, A dot dr equals 0 means that A is conservative, and if A is conservative, then its curl is 0. And its curl is B, so B must be 0. So obviously magnetic fields exist, so what went wrong here? If you remember our analogies, we had a water bottle for this one and a butterfly net for this one. And there's a very important difference between the two of them. A water bottle, as long as you have the cap on, is completely closed. You can't, you're not going to be able to hold a water bottle a direction and have the water fall out, provided that you have the cap on. But with a butterfly net, you just face if you put water in a butterfly net, well, if your butterfly net could hold water, there'd be plenty of positions where you could dump it out. And that's what's important here, is that you can't substitute in here, because for this part of the equation, we're talking about enclosed surfaces, which is why we could make that substitution. But then, between this step and this step, we're assuming that the surface is not bounded, or it is not fully enclosed. We're assuming it's an open surface. In fact, you can't really have a curve that bounds a enclosed surface, because it would just like go around the middle of the surface or something like that. But you can't have a curve that bounds an open surface, like the rim of a butterfly net. So that's essentially where the problem is. It's a little sneaky in how it's written because it doesn't write the limits of integration. It just kind of assumes them, which is something that can lead to problems like this. So the problem with the whole thing is the word enclosing. Thank you very much for watching, and hope to see you in the next video.